Evolution of generative AI.
The concept of generative AI emerged in the 1960s with early chatbots, attempts at creating AI that could engage in conversations. Advances in neural networks and deep learning in the 2010s enabled AI to learn to parse text and classify image elements, leading to a resurgence. The introduction of GANs by Ian Goodfellow in 2014 allowed AI to generate realistic images, videos, and audio. VAEs, introduced before GANs, played a crucial role in the advancement of generative models for AI. The development of the transformer architecture in 2017 paved the way for large-scale generative AI systems like GPT. OpenAI's GPT was introduced in 2018, representing a groundbreaking development in generative AI as a large language model. In 2021, DALL-E was launched for generating and editing unique artworks and photorealistic images. 2022 saw the introduction of open-source Stable Diffusion and proprietary Midjourney AI image-generating tools. GPT-4 was released in March 2023, capable of generating longer texts and expanding the capabilities of generative AI. The development of GANs and other generative AI techniques continues.
What is generative AI? Generative AI models learn patterns in data and use those patterns to produce new, original content. Generative AI is a type of artificial intelligence that can create new content rather than just analyze existing data. It can generate text, images, audio, video, or code, often in a human-like or creative way. Examples of what it can do: write articles, emails, stories, e.g., ChatGPT. Generate realistic images, e.g., DALL-E, Midjourney. Create music or voice, e.g., Synthesia, Suno. Generate code, e.g., GitHub Copilot. Caption medical images, e.g., Blip, CheXNet. ELIZA, one of the first generative AI systems. It was created by Joseph Weizenbaum in the year in 1966. It was a rule-based chatbot, not neural or deep learning, and it simulates conversation with a psychotherapist using pattern matching, i.e. DoctorScript, mimicked a Rogerian therapist. It used simple keyword matching and template-based responses and didn't understand context or meaning, just rephrased user input. E.g. example, user, I feel sad today. ELIZA, why do you feel sad today? It gave the illusion of understanding by mirroring what the user said. It has no real understanding, just surface-level tricks, very shallow responses, and couldn't handle complex or multi-turn dialogue. It is rule-based, completely dependent on predefined scripts, no learning or adaptation, and easily broke down. With unexpected input or ambiguous phrases, it failed quickly. The legacy of ELIZA is that it inspired development of modern chatbots and eventually LLMs. Early NLP models. Before deep learning, NLP relied heavily on statistical approaches. N-gram models predict the next word based on the previous N1 words. For a trigram model, I am going predicts 2. Its drawback is limited memory, can't capture long-range dependencies. Hidden Markov models, HMMs, used for tasks like part-of-speech tagging, speech recognition, and sequence labeling. These model sequences with hidden states and observable outputs. The drawback is relying on handcrafted features and shallow context. The legacy of early NLP model is formed the base for early voice assistants and spell checkers. 1990 to 2000s is the era of rise of recurrent neural networks, RNNs. RNN is a type of neural network designed for sequential data, takes prior input into account when predicting the next word or output, and maintains a hidden state that is updated at each time step. RNNs were important because these were the first models to handle variable length input sequences and could generate entire sentences with memory of prior words, unlike N-grams or HMMs. E.g. input, the dog is RNN processes this context to predict the next word, barking. The drawbacks of vanilla RNNs is that they struggled with long-term dependencies, information gets lost, and training instability, vanishing/exploding gradients. It was later improved by LSTM, 1997, and GRU models. The legacy of RNN is that RNN established probability-based foundations for NLP. This slide illustrates the architecture and working mechanism of a recurrent neural network, RNN, which is designed to handle sequential data by maintaining a hidden state that captures information across time steps. On the left, we highlight the memory capability of RNNs. The hidden state retains contextual information from previous inputs, enabling the model to capture temporal dependencies. In the center, the RNN is shown in its unrolled form, where each time step processes one element of the input sequence. The same parameters, weights W, U, and V, are shared across all time steps, which is crucial for modeling time-invariant patterns and reduces the number of parameters. The hidden state update equation and the computing equation of the output at each step are shown here. This shared, recursive structure allows RNNs to be used in a wide range of tasks like language modeling, time series forecasting, and sequence classification. However, standard RNNs struggle with long-term dependencies due to vanishing gradients, which later led to the development of LSTMs and GRUs. RNNs struggled with long-term dependencies due to vanishing gradients. LSTMs introduced gates, input, forget, output, and cell states to allow better memory retention over long sequences. Long short-term memory, LSTM, networks, a type of recurrent neural network, RNN, are designed to learn long-term dependencies in sequential data by using a cell state, hidden state, and three gates, forget, input, and output, to control the flow of information. This slide focuses on LSTM, long short-term memory networks, which are an advanced variant of RNNs designed to handle the vanishing gradient problem commonly found in standard RNNs when learning long-range dependencies. Variational autoencoders, VAE. In 2013, it was introduced by Kingma and Welling in their paper titled Autoencoding Variational Bayes. A VAE is a type of deep generative model that learns to compress input data into a low-dimensional latent space, encoding, and generate new data by sampling from this space and decoding it back. It's called variational because it uses concepts from variational inference in probability. It is like a regular autoencoder. A VAE has an encoder and decoder. But instead of mapping an image or input to a fixed point, it maps it to a probability distribution, usually Gaussian. During training, the model learns the best way to compress the data, mean and variance, and generate realistic samples from random noise. It samples from the learned latent space to generate new outputs. The drawback is VAEs often sacrifice sample quality and require careful training techniques. The legacy of VAE is that VAE influenced modern generative architectures, GAN, Stable Diffusion Model. This slide illustrates the architecture of a variational autoencoder, VAE, a generative model that learns a probabilistic latent representation of the input data. The encoder network maps the input X to a latent space by estimating the parameters of a multivariate Gaussian distribution, specifically the mean vector mu and the standard deviation vector sigma. Instead of directly using the latent encoding, a sample Z is drawn using the reparameterization trick. This trick allows gradients to flow through the sampling operation during backpropagation. The sampled latent vector Z is passed to the decoder network, which reconstructs the input X-. The objective is to minimize two losses. Reconstruction loss ensures X is almost equal to X-. KL divergence regularizes the latent space to follow a standard normal distribution N01, encouraging a smooth and continuous latent space for generation. The goal is to balance accurate input reconstruction while enforcing a structured latent space, making VAEs useful for generative tasks such as image synthesis, interpolation, and anomaly detection. Generative Adversarial Networks, GANs. In 2014, it was created by Ian Goodfellow and colleagues in their paper, Generative Adversarial Nets, published at NIPS, now NeurIPS. A generative adversarial network, GAN, is a framework for training generative models using two neural networks. Generator, G, tries to create realistic data, e.g., images, and discriminator, D, tries to detect whether data is real or fake. They compete in a game. The generator improves to fool the discriminator. The discriminator improves to better detect fakes. This setup is called a minimax game. GANs can create sharp, realistic, high-resolution images and outperform VAEs. GANs learned structured latent spaces that could be used for image manipulation, style transfer, and interpolation. No need to define an explicit probability distribution like in VAEs. GANs do not provide a clear confidence score for generated samples. GANs are hard to train and may learn to produce only a few types of outputs. The legacy of GAN is that GAN inspired hundreds of variations: DC GAN, Style GAN, Cycle GAN, Big GAN, etc. This slide introduces the Generative Adversarial Network, GAN, architecture, which consists of two competing neural networks, the generator, G, and the discriminator, D. The generator takes in a random noise vector, Z, transforms it into a synthetic data sample, G, Z, attempting to mimic real data. The discriminator receives both real samples from the dataset and fake samples generated by G, and outputs a probability indicating whether the input is real or fake. The two networks are trained in a minimax game. The discriminator, D, aims to maximize classification accuracy by correctly identifying real versus generated samples. The generator, G, tries to minimize the discriminator's ability to distinguish fake data, effectively fooling it. Training is done through alternating backpropagation, where gradients from the discriminator are used to update the generator, improving the quality of generated samples over time. GANs are widely used for image synthesis, data augmentation, style transfer, and super resolution, and are known for their ability to generate highly realistic outputs. Introduction of diffusion models. In 2015, it was introduced by Soldigstein et al. In their paper Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics, using the concept of generating data by reversing a slow-noising, diffusion, process. A diffusion model is a type of generative model that works in two phases. Forward process, diffusion, gradually adds noise to data over many steps until it becomes pure noise, and in reverse process, denoising, a neural network learns to gradually remove the noise, step by step, to recreate the original data. Once trained, it can generate new data, like images, by starting from random noise and reversing the noise process. It allows for flexible conditioning, e.g. text to image, image to image. It is much more stable to train than GANs and no adversarial game, just a denoising task. It is used in SOTA models like DAL E2/3, Imagen, Stable Diffusion. It requires powerful GPUs and long training time. The legacy is this model is great for guided generation, captioning, editing, interpolation. This slide illustrates the architecture of Stable Diffusion, a class of latent diffusion models, LDMs, used for high-fidelity image generation and synthesis. Process overview. The encoder, E, first projects the input image, X0, into a latent space, Z0, significantly reducing dimensionality while preserving semantic content. The forward diffusion process gradually corrupts the latent representation, Z0, by adding Gaussian noise over time steps, resulting in ZT. This process is defined as the reverse denoising process. It is learned using a U-Net architecture, which predicts the added noise, epsilon theta, at each time step, T, enabling recovery of Z0 from ZT. Conditioning mechanism. The model is conditionally guided by auxiliary information such as text embeddings, semantic maps, image representations, These are embedded and concatenated with latent vectors at each denoising step, enabling text-to-image or image-to-image generation. Denoising U-Net block. The denoising U-Net includes self-attention, Q, K, V blocks, and cross-attention layers to effectively capture spatial and semantic dependencies. The model incorporates time-step embeddings. Gamma, T, to inject temporal information into the denoising process. Decoder, D. After iterative denoising to retrieve latent space. The decoder reconstructs the final image. X0. From the denoised latent vector. Transformer. The transformer is a deep learning architecture that relies entirely on attention mechanisms to model relationships between input elements, without using recurrence, RNNs, or convolution, CNNs. It was introduced in 2017 by Vaswani et al. In their paper, Attention is All You Need. The purpose was to design for handling sequences, e.g., text, more efficiently than RNNs/LSTMs. Key components are self-attention mechanism, positional encoding, encoder-decoder architecture, encoder reads and processes input, e.g., a sentence, decoder generates output, e.g., translated sentence. Each block contains multi-head attention layers, feed-forward neural networks, layer normalization and residual connections. It requires massive datasets, can produce biased or hallucinated outputs. It is not interpretable without extra tools, e.g., attention visualizers, SHAP. The legacy is it is the foundation of modern LLMs and multimodal systems, GPT-4V and VLMs. This slide provides a comprehensive overview of the transformer architecture, a foundational model for many state-of-the-art NLP and vision language tasks. The visual layout includes 3 key sections. Encoder-decoder architecture, left section. The core transformer block consists of stacked encoder and decoder layers. Each encoder layer includes multi-head self-attention mechanism, position-wise feed-forward networks, residual connections, and layer normalization. Each decoder layer includes masked multi-head self-attention, encoder-decoder attention, feed-forward network. Positional encoding is added to input embeddings to inject sequence order, since transformers lack recurrence. Multi-head attention mechanism, center section. Demonstrates how input sequences are transformed into query, Q, key, K, and value, V, matrices. Multiple attention heads operate in parallel, enabling the model to focus on different parts of the sequence. The scaled dot product attention mechanism computes attention weights by comparing Q and K, followed by a softmax operation, and uses these weights to aggregate values from V. Self-attention mechanism, right section. A zoomed-in diagram of self-attention, showing the computation of attention scores and contextualized vector representations. Labeled as self-attention, it highlights how a token attends to all other tokens in the sequence, enabling global dependency modeling.
On this slide, we highlight some of the core technical strengths that make transformers so powerful and widely adopted in modern AI systems. First, parallel processing. Unlike RNNs which process tokens sequentially, transformers handle entire sequences simultaneously. This allows for faster training and better utilization of hardware accelerators like GPUs and TPUs. Second, transformers excel at long-range dependency modeling. Thanks to the self-attention mechanism, they can learn contextual relationships between distant words in a sequence, something RNNs historically struggled with due to their limited memory and vanishing gradients. Third, scalability is key. Transformers scale exceptionally well in terms of parameters and data. This scalability has enabled the development of massive language models like BERT, GPT, and T5, each pushing the boundaries of performance in NLP tasks. Fourth, transformers are incredibly versatile. They're not just used for text, we see them across various domains. In vision, with vision transformers or VIT, where image patches replace word tokens. In speech, for audio and speech recognition tasks. And in multimodal AI, where models take both text and images as input to perform complex tasks like image captioning, visual question answering, or multimodal generation. This slide introduces LLMs, large language models, which are at the core of today's most powerful AI systems. The concept of LLMs dates back to the early 2010s with RNN-based models, particularly LSTMs, which were capable of handling sequences with some memory. However, they were limited by their sequential nature and struggled with long-term dependencies. The real breakthrough came with the transformer architecture, which led to massive improvements in both model performance and scalability. LLMs are trained on large corpora of text to learn language structure, including grammar, context, and even some world knowledge. They do this through two key technologies: word embeddings, which transform tokens into dense semantic vectors; deep neural networks, specifically transformer encoders and decoders, which model complex relationships between tokens using multi-head self-attention and feed-forward layers. The diagram below illustrates this encoder-decoder architecture. The encoder processes the entire input sequence at once and encodes contextual meaning. The decoder generates the output sequence, one token at a time, leveraging both its own self-attention and cross-attention with encoder outputs. Positional encoding is added to retain order, since transformers don't have recurrence like RNNs. This architecture forms the basis for models like T5, BART, GPT, and more, which power tasks from translation and summarization to code generation and dialogue systems.
This slide presents BERT, or bidirectional encoder representations from transformers, introduced by Google in 2018. BERT is built on the transformer encoder architecture, and it captures context bidirectionally, which significantly improves performance on NLP tasks like classification. In the center, we see a typical text classification pipeline. The input text is tokenized, and token IDs, segment IDs, and input masks are generated. These are passed into the BERT layer, followed by a dense layer and a final classification head. To the right is the transformer block, consisting of multi-head self-attention, feed-forward layers, and layer normalization, all with residual connections. At the bottom, the self-attention mechanism is illustrated. It enables the model to assign different attention weights, for instance, giving more focus to relevant words like eating and green when processing apple. This is the core of BERT's ability to understand nuanced language.
Now let's look at how transformers have revolutionized computer vision, specifically through ViT, or vision transformers. ViT is a transformer-based model architecture designed for image classification and other computer vision tasks. It was introduced as a powerful alternative to convolutional neural networks, CNNs, which had long been the dominant architecture in vision. The key idea behind ViT is to treat an image like a sequence of tokens, similar to how transformers process text. Here's how it works. The input image is divided into fixed-size patches, for example, 16 by 16 pixels. These patches are then flattened and linearly projected into a vector space, effectively becoming visual tokens. A special, CLS, token is added to represent the global classification output, similar to how BERT uses it. Positional encodings are added to these tokens to retain spatial information, since transformers don't inherently encode order. The sequence of patch embeddings is then passed through a standard transformer encoder stack, as shown on the right. Each encoder block consists of multi-head self-attention, layer normalization, and feed-forward MLP layers. The self-attention mechanism allows each image patch to interact with all others, making it well-suited for capturing global image dependencies, which CNNs can only capture through deep stacking and pooling. In terms of performance, ViT has shown state-of-the-art results on benchmarks like ImageNet when pre-trained on large datasets. It outperforms CNNs by up to 4x in computational efficiency and accuracy when scaled properly. Additionally, ViTs offer better scalability and less inductive bias compared to CNNs, meaning they can learn more general features when trained on large amounts of data. Despite its power, ViT has trade-offs. It requires large-scale datasets or pre-training, e.g., on JFT300M, to match or exceed CNN performance. However, newer adaptations like DAT, data-efficient image transformers aim to reduce this data dependency. In summary, ViT marks a significant shift in how we approach computer vision, leveraging the power of transformers to move beyond the local receptive fields of CNNs, and enabling global reasoning over images with less computational cost. Next, let's delve into BLIP, which stands for Bootstrapping Language Image Pretraining, a powerful vision language model (VLM) architecture. BLIP is designed to bridge computer vision and natural language processing by jointly learning from image-text pairs. It supports two main tasks: vision language understanding, such as visual question answering (VQA), vision language generation, such as image captioning or text-based image retrieval. BLIP leverages the vision transformer, ViT, as its visual encoder. Here's how it works. An image is split into fixed-size patches. Each patch is linearly projected into a high-dimensional embedding space. These patch embeddings are combined with positional encodings to preserve spatial information. A CLS token is added to represent the global image feature, which is especially important for classification or summarization tasks. The transformer encoder processes these visual tokens using multi-head self-attention, which allows patches to attend to one another and extract meaningful global features. MLP layers, layer normalization, and residual connections, all typical of transformer-based architectures. What makes BLIP particularly effective is its dual pre-training approach. It uses a vision language contrastive learning stage to align images and texts, followed by captioning and image text matching tasks to learn generative and discriminative capabilities. This combined strategy enables BLIP to generalize well to both understanding, discriminative, and generative tasks, making it highly versatile for multimodal AI. BLIP's performance has been strong across multiple benchmarks, outperforming many earlier models in tasks like COCO captioning, VQA, zero-shot image text retrieval. Its architecture has also laid the foundation for more advanced models like BLIP-2, which incorporates frozen language models and cross-modal adaptation. In essence, BLIP is a prime example of how transformers and ViTs are being extended beyond single-modality models, pushing the boundaries of multimodal AI where vision and language are deeply integrated. Now, let's take a deep dive into GPT, or Generative Pre-trained Transformer, a foundational model in the field of generative AI and natural language processing. GPT is a decoder-only transformer model, designed specifically for autoregressive language modeling. It predicts the next token in a sequence based on all previously seen tokens, a process referred to as causal, or masked, self-attention. The architecture, as illustrated on the slide, consists of multiple stacked decoder blocks. Each block follows this structure. Masked multi-head self-attention ensures the model can only attend to previous tokens, maintaining the left-to-right generation flow. Add and layer norm adds residual connections followed by layer normalization for training stability. Feed-forward neural network, MLP, a two-layer fully connected network applied to each position independently. Dropout layers help regularize and prevent overfitting. The input tokens are first converted into token embeddings and summed with positional encodings, which are necessary because transformers have no inherent notion of word order. Pre-training phase. GPT is trained on massive unlabeled corpora using a language modeling objective, predicting the next token in the sequence. This enables the model to learn syntax and grammar, semantic context, world knowledge implicitly encoded in text. After pre-training, GPT can be fine-tuned or used in zero-shot, one-shot, or few-shot settings via prompting, making it highly versatile. With models like GPT-2, GPT-3, and GPT-4, we've seen exponential scaling in terms of parameters, enabling advanced capabilities such as long-form text generation, code synthesis, reasoning, and even multimodal understanding, as in GPT-4. Today, the term GPT has become synonymous with generative LLMs, as many large-scale models adopt this underlying architecture and training strategy. In essence, GPT's architecture showcases how large-scale unsupervised pre-training on transformers can unlock powerful, flexible AI systems capable of reasoning, generating, and understanding language.